My name is Dr. James Haworth. I'm an associate professor at UCL, and I'm one of the chairs of the ISPRS Commission for Working Group on GeoComputation and GeoSimulation. And I'm very happy to announce that we are joined today by Professor Tao Cheng. So Professor Tao Cheng is the director of SpaceTime Lab in UCL. And she's one of the pioneers of spatiotemporal data analytics. So over the past 10, 15 years, she's been one of the leading figures in dealing with methods and tools for spatiotemporal data. Worked on many large projects, including with Transport for London, working on their traffic data with the London Metropolitan Police, working with crime forecasting, and more recently working with COVID-19 data in a large project called Virus Watch. And later on, Professor Tao Cheng will be joined by Seula Park, who's a visiting researcher in SpaceTime Lab, and she's interested in graph databases, how they can be used to represent spatial processes and spatial networks. And she'll give some case studies of the work she's doing with that. But first up, Professor Tao Cheng will talk about the work she's been doing recently, which deals with the network and graph structure of spatial and spatiotemporal data, and how we can develop algorithms such as those based on deep learning and the latest advances in computer science to apply to spatial and spatiotemporal problems. So without further ado, I'll pass over to Professor Cheng, and thank you very much, Professor Cheng. Over to you.
Thanks, James. Thanks to ISPRS and for all the colleagues able to put the workshop very quickly, and also welcome to everyone, especially for those come from China or Chinese people. It's really the Saturday of the Chinese New Year, so no matter where you are, good morning, good afternoon, or good evening, and happy long year of Tiger. So I'm going to talk about the work that James mentioned in the past, probably say past 10 years with space-time analytics or space-time AI, and especially we developed based on networks. So I'm going to talk, because the time is quite limited, so I'm going to talk about 40 minutes about the concepts, actually a little bit the methods as well, and how we applied it in terms of the methodologically for prediction, clustering, and some spatial analysis and optimization, and also in terms of transport, crime, health, so that I can give you some flavor of the work we are doing. And then, yeah, and I will say more about what I think about where we should go in terms of this direction. And also now I pass to Seula, which quite close linked to my talk. So, whenever I give talk, I think most of the nowadays we will start from these slides. As you know, especially at this pandemic period, although I hope we're getting out of it. So Dr. John Slow is, I think he manually used his hand, draw this map about the situation of cholera in central London. And he found the association of this wheel of the residents who has caught the virus. So this is a Broad Street pump, and it's really very close to UCL. So we were thinking that's the starting of spatial analysis, right? So that's the origin of spatial analysis. So from 1854, we have traveled very, very far. We go from there, we have our first, say, D system, first forest information system, then to what we call now big data period. We have Internet of Things, we have a cloud-based system, we have, of course, we have web, we have Internet of Things, we have cloud, we have big data, we have AI, then 5G. Now, so actually what do we have for the information? We have location, we have time, we have content, and then we use the term smart cities, Then we have the GeoComputation, smart cities. Then some people call us spatial data science. Then we have data analytics. And I know some people like use the term GeoAI. For me, I want to use SpaceTime AI. Why? Because although most of Geo really focuses on the spatial bit, actually lots of things is dominated by temporal aspect as well. So that's why we want to have integrated spatial temporal modeling. And because last year we have a new term, metaverse. Okay, so what is the metaverse? Okay, I mean, there's so many definitions about that. For me, fundamentally, it involves clouds, have Internet of Things, so they have what they call the beam, they have analytics, and also virtual reality in that sense. So fundamentally, all these things, is the data showing somehow here. So what does that mean? It means to say, oh, sorry, I already showed you the other one. Yeah. So it really means to say, now actually everything is connected. So network is indeed everywhere. So for us, I think for us, most people have to deal with transport network. And then some people dealing with social media data, some people also dealing with citation networks. And of course, now we talk about energy, we talk about autonomous driving. So interconnected to everything. Of course, as a beam, as a digital, yeah, I missed one more word, digital twins, right? So 3D clouds, point clouds is actually the data really within those regime. So all of that really means to say, now network is everywhere. Of course, I haven't mentioned about the other domains. So that's one of the reasons I think I'd like to talk about, say, with networks. So what do we have in the past? As I said, we're looking back from the Dr. John Slow's period to now. Fundamentally, I think this is some. You can see a lot from this track, from SI in SRS ArcGIS software. So basically, fundamentally, we want to represent the real world, right? So conventionally, we think the world, we can either call them as a feature same or grade same. So in practice, we use point, line, you may say this line, polygons to represent the objects. So you have two data format to represent them. So one is called vector-based, so it really shows the coordinates of them. Another way we use rasters. So we divide the space into uniform, small grids. So in this way, we can represent the real world. Okay, so now if everything is a network, so how are we going to represent the real world? Although I think if any of you guys are GS students, you must learn the network-based structure. Fundamentally, it's a topology. You talk about the connection of your geometries. So if the point and line polygons, we define the polygon is made of lines made of points, then the loads, okay? So if it's a network, we really define it is to say, we have, say, for example, we know they are connected. But then how we do it, actually, we can convert it into graph. So this is called, if it's network, they have the words. So this is the, say, in the network, we have load, A, B, C, D, and then have link. So B, C, A, C, all the links. But if it's graph, you have point. Same thing, this is graph, and then we call them vertex, okay? These are the loads, so vertex, and then we call them edge, okay? No matter what it is, we use adjacency matrix to represent it. So really talk about the linkage of this loads or vertex. So very simple, isn't it? So that means to say we are able to convert networks into graph. Equally, with this structure, we can convert the world data into graph. So in this way, in this way, you can see these loads, we can use graph to represent them. Once we have the graph, then we can represent them using spatial adjacency matrix. So in this way, all the world data, no matter which format they have, we can use network-based approach or graph-based approach to model them. So that's, let's say, firstly, it's possible. Two, what's the advantage of it, right? Why bothered? So before I go that, I want to put one more thing here. So when we talk about the space-time, I was talking about space-time. So we'll talk about the processes. I want to clarify how we define them. Actually, I always divided them into two situations. One I called length. So it's called the space-time series, which is not of the series we have been observed in real world, like a transport, like a finance, like the population of places. So like the data you can always observed. But this other situation is we call sparse, or called the sparse space-time point process. It's very sparse, like I said, it doesn't appear all the time like the incidents, such as a crime incident or traffic incident, or even like some fire incidents. So for both of them, you can always say, actually, we can always somehow differentiate them. Why is called them in the temporal domain, and another called the spatial domain. So in this way, that's the one we talk purely about the spatial units in 2 dimensions. But now we talk about the space-time process in 2 dimensions. So that's the temporal aspect, that's the spatial aspect. So what I'm trying to say, that means to say not only spatial data, but actually spatial temporal process can also be converted into a network-based or graph-based presentation. So that means, say, we can, once you converted them into graph, then into the network, then you can really use the graph. There's a 2 ways to make this graph. I mean, if you guys know anything about graph theory, you should know this. So that means, say, we can use the loads in the real world as the vertex, or we can use the link or to the vertex. So it's 2 ways. Okay, I'm not going to any detail. So fundamentally, so what is graph-based modeling? Basically, you put all the information on the vertex of the graph, which is called a singular. So you're trying to model, this is mostly representing the temporal information, and trying to model the change with time, but equally, you're trying to understand the connection of 2 loads or vertex. So that's the edge. So in this way, you're trying to model their spatial or association or correlation. So that's how it can be done. So we said that it's possible. So why we bother? We have so many ways already we can representing them as rasters, other structure. So for me, I think there's few advantages, especially for urban studies, use network-based approach. First one is really fine granularity. So this fine granularity basically make it prediction much more accurate. And more importantly, as we all know, when we try to convert the original information into raster-based approach, we need to define the size of the unit, which you call the spatial resolution. So once you have to define different size of it, if you have a different resolution, your outcome might be different. So that's quite associated with what the multivariable area unit problem. So what's the consequence of that? You should study about it. So you can have what they call the ecological fallacy. So that means to have different unit or processing, you will have different outcome. So I personally think is that using network-based approach can avoid this problem. And because it's fine granularity, of course, when we do the analysis, we can make it more accurate. And most approach we're taking, we can say, great network-based approach give it much better prediction accuracy than the grid-based approach. And in terms of the usability or practicability of the graph-based approach, because as I said, in urban studying or urban life, people working around the networks, police don't walk around the blocks, they really have to follow the line of the road. So that's why, and also when you do the prediction of the traffic, if you predict them on the grades, really push the traffic flow to the place there's no traffic. So that doesn't really help. So, but if we can align everything around the networks, it makes it much more useful. So that's one of the few reasons. Of course, one more reason, I think quite important reason, when we talk about space-time AI, is lots of approach, is especially the latest deep learning approach, actually now is graph-based approach. The reason for it, as I said, graph, I think later on, when Seula talk about graph-based database, or you can understand actually lots of the good characteristic of a graph enable the flexibility, make network dynamic, and also in terms of the deep learning, graph-based deep learning is the currently most latest advance. So to be able to fully embrace the advances in machine learning or AI or deep learning, I think we should really think of make use of the converting our spatial structure into graph. So that's kind of the work we have been done in the past years. So now let's very quick brief introduction about why we want to use graph and how we can use graph to represent the spatial data or spatial temporal process. So in the next half hour, I hope. So give you some example and say how this can be applied for space-time analytics. So I will start with space-time prediction, because that's one of our I think the strength of our team. We did lots of spatial temporal predictions with various applications, as I mentioned in the introduction of James. So how we approach it. So if we use graph-based approach, fundamentally, we need to define the network topology, like we have done in all the GI systems. You have to define the topology, which is based on geometry. And again, because the data is repeatedly observed, have a historical data, so we call the temporal data. So we have to convert them into graph. So as we described already, graph actually is the vertex or loads and the edge. So I've already explained you really have to understand the spatial temporal dependency of the data, so you can model them, right? And then we also explained to say the process have sparse and dense. So that means we might need to choose different ways to define what they call the temporal dependency or spatial dependency. And of course, make it more complicated, as we know, lots of flow like traffic or energy or even water, they have direction. So you need to define directed or undirected topology. And another very important issue about deep learning, because large volume of data, you want your algorithm is most effective so that the city-wide analysis or prediction could be implemented. Otherwise, it can only be studied in your lab and never really be useful in the real world. So, of course, if no matter which method you're using, especially with deep learning, so that you want to have the high accuracy and high computation efficiency. So that's the kind of the framework. Actually, this is summarized by my student, Dr. Zhang Yang. Okay. So to do the deep learning, use deep learning for space-time prediction, I need to mention, I think, two things, because fundamentally we need to model the temporal dependency and the spatial dependency. So let's look what is available there, the tools from machine learning alone. I think if anyone working on this domain, you'll be very familiar with this one, long short-term memory. This is a tool, it has been most popular, I would say, in the past years to model any time series. So this is fundamentally start with time series and also actually widely used for natural language processing, like translation. And they have other two forms, recurrent neural network or gated recurrent neural net. It's just, I think fundamentally they're trying to use a strategy or mechanism called gates, and also feedback approach to improve the learning. I'm not going into detail of that. You guys, if you don't know, you can. So fundamentally is the mechanism of gate, make it powerful to learn. And another one, if we want to model spatial, is really have to think about the spatial dependency. So I think the early stage, most popular one is called the CNN, convolutional neural network. So if you have done image understanding, is very similar approach, we have convolutional analysis. So fundamentally, it tries to borrow the information of your label. So no matter use tree labeling or line or big labeling. So basically, it's to maximize your learning efficiency. So this is really means to say you have to divide the space into regular grades, and it's really being used for your declining space. So again, because it's rated approach borrowing, I think borrowing from image processing, so has been used tremendously in visual object recognition or detection. I think in geoscience, I mean, about we have another big piece of work is using computer vision to understand urban or cities. We have literature on that. And another group has been using this for land use, and some people used it for object detection. So in our domain, so it has a great use. So now another one is I think in the past 3 years, 4 years, graph convolution network is another thing. It started, as I said, lots of data is irregular data, and they are a lot in the Euclidean space. So like a biology, chemistry, social network. So that's why they develop what they call the graph convolution network. I personally think they're very similar. I'm trying to tell you why for this GNN and CNN, because our work actually first use CNN and then later move to GCN. So fundamentally, for spatiotemporal deep learning, no matter what you do, we can always put them into four ways. So some is kind of integrated. So that means to say I take a temporal framework like LSTM, and then some say I fundamentally take spatial. I put the emphasis on spatial bit. So you put the operator into the other dimension. Another way to say we can first focus on spatial aspect, then we focus on temporal learning, or the other way around. So no matter, I know in the past 2 years, I think it's lots of papers have been published. No matter what they are, fundamentally, I think they all the kind of variation of the two forms I just mentioned, CNN or GCN or L and short memory learning, and the combination of them. So I'm going to use a few examples we have developed. I personally think we are the very first to develop the network-based deep learning, the very first, but also the very first to use network graph deep learning. So I want to introduce to you guys how we approach it. So when we did this work, it's published in 2019, but we already started 2018. So how we approached it, because the work originally really used, a lot of people use CNN, everyone converted into the grade-based approach, as I said, which I don't think is suitable for traffic prediction. So we say why we cannot use the network-based approach. So we took a network-based approach. But even so that time, most of the approach we available is to use the CNN convolution. But we say why we cannot change it. So we use the approach called localized CNR, which use residue. So fundamentally, what we did is say we define the spatial dependency using spatial adjacency matrix. Okay. So in the convolutionary CNN, you have to do the full connected convolution, but we don't do it. We use the spatial adjacency to do the convolution. That means we localize it, so not all of them are fully connected. So in this way, I think it improved the efficiency of computation and the convergence much faster than you use a fully connected CNN. And then also this enable, we are able to use the network as the node of the neural network. So fundamentally, so this has been, you can read the papers. Fundamentally, it's still take or long short memory learning. So it's say capture the weekly, daily, and also hourly patterns. So it's fundamentally, it's still time series approach. But then we integrated the spatial learning into it. So that's it's called a residue-based local convolutional neural network learning, kind of like that. So in this way, you improve the efficiency of the convolution and also improve the accuracy. And most importantly, it's a network-based approach. So after we done this one, now we say actually why we cannot use the graph directly, because for that one basically, even if you define network, it's like a graph, but fundamentally we still define different spatial adjacency metrics. But the graph fundamentally is defined automatically. So that's why we, in our next paper, we changed it. We used to completely embrace the concept of graph. And again, because the temporal dependency is stronger, that's say for all the transport modeling, okay? So that's why I can say lots of approach of transport modeling have to take long short memory as a fundamental structure, but then they integrate the spatial learning in it. So this one is very similar, but that one said we used the W in the previous paper, use the spatial adjacency. We define it explicitly, but in this paper, it learned it automatically. So that's the major difference. As I said, the network can be directed. So our further development is define a graph, which is called a very behaved graph, to represent the direction of the networks. And more than that, we make the flow, the dynamic flow, more intelligently use Markov chain to represent how the flow at this junction be divided. So this, I think, is a highly readable paper of that journal. So that's the latest of the traffic prediction. I think probably from my perspective, I know there's lots of latest development. As I said, is various combination of the learning approach, either from temporal aspect or either from spatial aspect, but fundamentally they are very similar. So look at the case study. So this is the case study we use, I think, in these 3 papers. So this is, we use text data can be provided by DD. Intent to is natural road network, and we convert it into graph, as I've said, and then to look at the performance of this algorithm. It can do whole citywide prediction, and most importantly, if the flow is high, the accuracy is high. So this is very important, because you know when the flow is low, that means it's low congestion. So you don't really care in that sense, because you can travel free. But if it's highly congested, you really want your predictions more accurate. So that makes sure you really know if it's going to be congested, how's the situation, as you can see. So that's one of the strengths of our work. And again, when this incident happened, you may say, highly congested situation, we don't need to have pre-processing. Not the people now for the conventionally transport modeling, they like to differentiate different stage of the traffic, which is time consuming and more also very subjective, and it's not easy. So if you have to do lots of pre-processing, which is not realistic with large network, and so the whole process is fully automatic, and that is high efficiency for the whole citywide prediction. So I think this is a highly effective algorithm to work for large network. So this is for transport, okay, and then for crime. As you know, we have working on this crime prediction also very long time. In the early stage, we develop what are called network-based kernel density estimation method to infer the hotspot and road network. Even so, we found it's really time-consuming and also need to infer lots of parameters. And for updating, it's very, very, very slow. So let me see why can we use deep learning to tackle this problem. So the challenge we're facing, okay, compare these two processes. One is time series, another one is called this point process. So it has sparsity, not only in time, and also in space. Again, we have to put them into networks. So if you do deep learning, you understand that we call it called imbalance regression any problem, because the data is so sparse, and really means you have to use different weight for different position and or time. So again, I'm not going to go to detail. So fundamentally, what we did is that we first focus on the temporal learning, temporal dependency, and then we put them into spatial one, and then we put them together, and then we generate the outcome. Because the paper is published, you could go to read it. So this is fundamentally we use what we call the gated localized diffusion network. So basically means I've already explained the gated is the one to be used in non-short memory deep learning. And the localized is really to dealing with this imbalanced problem. And so in this way, because the imbalance is in both spatial and temporal dimensions, so we have to use them for both dimensions. So if you look at the outcome, so you can see this one is also achieved much higher accuracy and the same thing high efficiency, computation efficiency compared with even our latest network-based KDE. So if you say, for example, say this is compared to method use the open data in Chicago crime dataset. So I don't know if you can really say it clearly. So the green dot really means say we are able to, those are the real crime data set which are appearing at the hotspot we predicted. And the blue dot is the one probably we're missing. So if you look at this, I think this is top 10% or top 20% of the hotspot. So that means to say among for this particular day, we have 1, 2, 3, 4, 5, 6 crime, but one of them are missing and 5 were captured. So the hit rate is 5 out of 6. But if you look at this one, same thing, but they are missing 3. So the hit rate is 3 out of 6. So similarly for other crime types. So so far, I think that's I haven't seen any other methods or any other work really use this deep learning approach to predict this sparse event. We have also applied it for fire or traffic incident, and they all works. The final case about prediction, I want to go very quickly. It's about a healthy data set. This again is a little bit early last year work, and at the very early stage, we do we want to focus the spreading of the COVID-19 and globally. So we use our use data. As I said, it's early stage. It's really early stage. Use the 5 months data, and then thanks to the data provided by our colleagues in Johns Hopkins University, so we're able to quickly access the data set. So for us, there's lots of things we can choose. We choose population density, and also because we think the virus really transmitted within cities, we choose urban population, and more importantly, we think the young people are the main reason the virus are transmitted. So we use fertility rate to be one important features. And because the transmission also relevant to government policy. So I think Oxford, they have defined the index of government response. So we use some of the index. Of course, at that time, there's no open data being used for national and international travel, so we cannot able to put them into the model. So the whole idea is basically we use graph neural network And again, we use long short-term memory to be the, as I said, we think it is very strong temporal dependency among the transmission. And especially, we needed to learn the spatial dependency. But this one, we use a new, I think this is getting popular, I think in the last 2 years. It's called VAE, variational autoencoder, to learn the spatial dependency. And then we make prediction. So again, this paper has been published, you can read it. So this is just to say, I want to show you graph-based deep learning is powerful. It's very flexible. You can choose different ways to represent your spatial dependency or temporal dependency, no matter it's dense or sparse. Now I think let me see, what time is it? Yeah. So I think in the next few minutes, I want to show you something else. I know we do lots of space-time prediction, but actually space-time analytics or space-time AI not only about prediction, because sometimes we need to do clustering or profiling and also other things. So I want to show you a few examples, which also have been done by my PhD students. So this is the work by Jialan. So this is really what we do. We use some police movement data. This is showing here in space and time, trying to understand which place at what time they go most. Normally we call it space-time region of interest. So I think lots of people working on those topic as well. So based on their GPS tracks, we're trying to classify or clustering where they go most and what time. So this is what they call it. This is use kernel density. Okay, so we can identify this all the place they go. So as you can see, this is kind of raster-based approach, right? So actually, we can also do network-based approach. So everything we do is around the whole clustering as around the network. So you can really identify precisely which street and what time they really visit. And also we can also assign the semantics to them. So this has been done. So yeah, so that's equally, that means it's much more accurate and much more intuitive to navigate, to understand, and much easy to assign the semantics to this space-time ROI more accurately. So this is for the case for clustering. Another one, and a lot of people can use social media data to try to understand what's people's interest or land use, lots of things. So this is the work by Jun Tao. So this is, he used Twitter data to understand, what's the, you can say land use or what's people's interest in London. This is the Council of Camden, which way this is Camden Town. So you say it's somewhere here. So lots of people use what we call space-based approach. So basically, this is what you call polygon-based approach or census block-based approach. So this is, just aggregating everything into this. Another one, again, most people use this graded-based approach. Okay, so for different, little blocks, how it look like. Okay, again, we can use network-based approach. I personally think this is useful to say, hey, which street is really full of entertaining, or which street is really, people enjoying the food, and equally this can be applied to which street people cycle most, or which street, have most coffee. So personally, for me, I think you can really understand what's going on for each road, because it's sort of for those blocks doesn't really mean much. Last one is not least, because time is so limited. So this is a work by Huang Fa. So he has been working around how to do intelligent policing. This is one bit of his work. I'm just give you some flavor. So how you design the patrolling district. Conventionally, again, people use graded-based approach, or people use a census block. But again, why we cannot make it more accurate, more intuitively around the streets? So that's his work. He used tuber search to really make sure each block, which represented by different color around the streets, they can be patrolled within equal time, because the police resource is very limited. So the one that they can finish the patrolling at the equal time, and that means that they walk more or less same distance. And of course, you can choose the ways to define the optimization criteria. So I think that's, I hope, very short. I hope I gave you some kind of idea about what can be done with network-based approach. So in summary, I think in the era of the interfacing, or in the new era of the metaverse, I think network-based analytics is needed, especially for advanced studies. And the graph or letter-based approach or graph is structure that can represent point line or area or networks, which we are all, or even Grace, we're all very familiar with. And I have showcased using graph-based deep learning for space-time prediction in relatively detail, and also which has been used for transport, traffic flow, and crime incident, and health and prediction. And I also give you very briefly about how this network-based approach can be used for clustering, to detecting the region of interest. Region not only on the different census block, you can also focus on different street levels, and also for optimization, and also for Twitter data analysis. So I hope through those cases, you're able to say network-based approach are really able to embrace lots more real-world applications. So like energy network and rivers, and and of course for autonomous driver networks. I was also really highly thinking we need new tools for network-based approach. Not only from data presentation to management, to analysis, and the things we have saying here. So that's why I think in the next half hour, I think Dr. Seula Park will explain to you. That's another work I would like to do, say use graph-based database. Why is more powerful than what we got in many relational database, and to improve, to really embrace, the digital term, metaverse, or whatever new terms we're using, so can really advance space-time AI. So James, I think I'm going to stop here. Thanks again for all the audience here with me this morning. I'm in London, so thanks.
Thank you very much, Tao, for that excellent overview of both the tools that are available in this area of research, and also some of the applications that you've applied your work to. So we've got an hour and a half for the session. So we do have a bit of time for questions if anybody wants. And while people are writing those, I have a quick question for you, Tao. So I think looking down the list of participants, lots of them are early career researchers, so perhaps MSc students or PhD students, or maybe postdocs who are thinking about what their career will have in front of them. So I was thinking, do you have an idea for what the next 5 or so years of research might be in this area, and any recommendations you might have for them if they're starting their research careers?
Okay, thanks, Jim. I think, as I said here, I think network-based approach or graph-based approach, although we are not unfamiliar with it, but most of the work in GI science, if that's the audience have, or if it's the ISPRS group, lots of it's about routing. But I think it's not about routing, okay? Graph is not only about routing. there's so many other things is relevant. For me, I mean, right now, if we talk about within digital twin, within metaverse, or BIM, I think, say, there's lots of networks around us. And each network is unique, but they have some commonality as well. So like how we presenting them, and more importantly, how we representing the interaction among these networks. So there's a concept, lots about the network theory, multi-layers networks. I think that's the work we are focused on right now. And for lots of work about the human mobility recently, I think lots of work, especially related to COVID. Again, I think they could be more bring more into network-based approach, because fundamentally, as I said, the people working around networks, not the grids, not census blocks. So really, I hope people really can start off thinking of, say, shifting the perspective from conventional raster-based approach or conventional other approach, more in the networks, more use the graph-based approach, thinking about the world and think about what we need to develop to understand the fundamental process, not only in the data, but the process behind it, and how we can represent the process. Only if you understand the process, you can really make a good prediction. And more than that, how we make an optimization. Fundamentally, we want to know what's going on, what's going to be in the future, and how we can make the future even better. So how we're optimizing what we have now and to guide our decision making. So GeoComputation, geo-optimization, and the geo-decision making, I think that's the approach we should take.
Thank you, Tao. So we're not getting any questions in the chat at the moment, so we can come back to that at the end. I think in the interest of time, we can pass on to Seula Park. Seula Park is from Seoul National University, and she's currently visiting in SpaceTime Lab in UCL. And Professor Cheng and Seula are working on some graph representations of spatial data, and in particular in database representations. And I heard an extended version of this talk end of last week, which was really, really useful for me as a kind of mid-career researcher who doesn't get to connect with the technical things so much anymore. So hopefully, if you're new to graph databases, then this will be a nice introduction to them for you. So over to you, Seula.
Thank you, James. And I'll share my screen first. Okay, can you see my screen?
Yeah.
Okay, then let's begin. Good morning, everyone. I'm Seula Park, and I'm a postdoctoral researcher in Seoul National University. Now I'm doing visiting research in SpaceTime Laboratory at University College London. Currently, I'm studying about graph database focusing to Neo4j, and I'm trying to use this database in my research for managing spatial information. And today, I'd like to talk about graph database focusing to the application in spatial fields. First, we can discuss what the graph database is and advantages of graph database compared to the relational database. Then also, I will introduce several utilizing graph database for spatial application by reviewing various researches, including my current research as well. Okay, let's begin. Before talking about the graph database, I'd like to talk about the property graph data models. Graph database uses the property graph model as a standard data model, and the property graph model is composed of node, relationship, label, and properties. This figure represents the log relationship between then and and. The bottom command expresses those relationships between two persons using the cipher, which is the query language of Neo4j graph database. Then and and are the nodes in this model, and they are included in the person groups. Those two nodes have the property of names as well. Like this, nodes are the entities in the graph. They can be tagged with labels, which is representing their different roles like this person. And also they can hold any number of properties using key value pairs like these name properties. And nodes can be connected with various types of relationships as well. For the labels, they can represent groups of nodes with similar properties or roles. Relationships provide directed named connections between two node entities like the loves in these figures. They can have a direction and a type as well, and also similar to the nodes. In the property graph model, relationship also have properties as well. Graph database is a database based on the property graph model that I mentioned just before. As large amounts of irregular and unstructured data, such as images, sounds, or some kind of textual information are required to use. However, a relational database has relatively strict schema. Therefore, it is a bit difficult to cover those various types of data with only relational database. Graph database is kind of a NoSQL typed database, and it is useful for finding the hidden meaning or patterns by analyzing the relationship between objects which is stored in graph database. Elements of graph database are graph storage, which is for the storing the graph data, graph processing engines for the processing queries, and graph query languages such as Cypher. Let's talk about the schema of graph database. Graph database has a flexible schema, so it is really flexible to add, change, or delete the data from the existing graph database. For the relational database, if you want to add a new data with the new attributes like these figures, first you need to add a column to the existing database, and then you need to check the tables while linking the foreign keys from other tables, and then you can add values and constraints of new data to the existing database. However, in process of these changing, it is easy to occur some kind of model denormalization, data consistency problem, or some kind of unnecessary null value generation like this figure. Let's move to the graph database. If you want to add new data to the existing graph database, you can just add a node with the new properties like this yellow node. Then just connect the newly added data with other nodes using some specific relationships. Then you can apply single or multiple labels to edit node for easy management. There is no need for iterative work of searching and editing the entire tables because graph database stores each record as one object rather than inserting it into a structured table. It means it is independent for increasing data volume, and also it can respond to the variety of input data forms. In this context, the load for organizing database schema is quite low for the graph database, and also high flexibility can be guaranteed in terms of data operations. For the next, I'd like to talk about the performance of querying while using the graph database. For the relational database, as queries become more complex, multiple joins between many tables are required like these figures. When using the relational database, you need to search all table data from the first record to the last record when performing consecutive joins on multiple tables because we need to find some common values to be joined. Larger the data volume to be queried, it means the speed and performance of query processing must be lowered using the relational database. However, for the graph database, traversing the relationship between objects and retrieving only the necessary data are required like these figures. You can just find the starting object, and then we can search data following the connections like these red lines. Performance of querying using the graph database is determined by how many nodes and relationships the query touches. This figure represents the real activity occurred in the real world. And for the graph database, the basic data model looks really similar to real world like these figures. So it means it is easy to understand data model and the structure of data, even the information is unfamiliar. Therefore, data intuition can be guaranteed while using the graph database. For the relational database, the process of transforming the real-world data to those like the strict form of table are required. Therefore, data intuition is lowered compared to the graph database. But make sure it does not mean that graph database is always better than the relational database. It depends on the data and the purpose of your modeling. We've talked about strengths of graph database, but I've already told graph database is not the best for all application or analysis. So where to use the graph database or where cannot use the graph database? As described so far, there's no performance degradation as the data size increasing. And also fast speed in traversing connected patterns can be guaranteed using graph database because they ignore the non-matching patterns while querying. Therefore, graph database is quite useful for a complex query using multiple tables because they don't need any kind of complex join process between many tables. And also, it can be used for tasks focusing on the relations of multiple data based on their structure of graph. Because of its flexibility, graph database can be used for the integration of various types of data as well. However, for aggregate-centric queries, graph database is not the best. For example, simple queries like, how many members in these working groups? To get the answer from these questions, relational database is better. On the other hand, when querying the relationship between distance object or data using n hops, simply like what is the relationship between SpaceTime laboratory and UCL? Like these relation-based analysis, then graph database is advantageous. And also, graph database is effective to handle the relation-oriented data. Therefore, we do not use the graph database when there are many unconnected nodes as well. Relational database is more efficient to manage a kind of log data, and also it is more appropriate to data, including very long attribute values as well. Let's move to the Neo4j. We've talked about general things about graph database so far. For the next, I'd like to talk about Neo4j briefly, which is one of powerful graph database. Actually, there are several graph databases nowadays. Neo4j is one of them, and it is an open source NoSQL native graph database system. We can use Cypher for querying and managing data in Neo4j system, and constant time traversals in big graphs for depth and breadth can be guaranteed in Neo4j, so it means Neo4j can show some great performance for querying graph data. Following to the characteristics of graph database, Neo4j has the flexible schema as well, so it is flexible to manage various types of data. They can provide drivers for several programming languages such as Java, JavaScript, Python, etc., and also they support to develop own procedures and functions for the analysis based on the graph theory. Then what can we do with Neo4j? Basically, many graph algorithms are implemented in the Neo4j, such as pathfinding, centrality, or some kind of similarity analysis as well. And also, they provide some kind of machine learning models for the task of node classification and link predictions as well. Like this example, multiple analysis functions are implemented in Neo4j in the form of library. And also they provide some kind of various analysis apps as well. And if we want to use those kind of apps, we can use it after installation of those kind of apps into the Neo4j graph database. For the focusing to the spatial application, I'd like to introduce a library of Neo4j Spatial. This is a library of utilities for Neo4j that enables spatial operations on that. Basically, we can import kind of CSV, XML, or some kind of relational database to the Neo4j graph database. Using this kind of spatial library, we can import SVG file or OSM files as well. And also, spatial queries for topology operations such as contain, intersect, or overlaps, or what else, they are implemented in the Neo4j spatial library as well. So we can use this library for many spatial queries to do some operations about the topology. We all have needs of managing spatial information in our research field. So from now on, I want to talk about why graph database can be used for spatial applications with several examples as well. Almost every entities in real world are connected spatially, and we can think about the most infrastructure such as road or bridge. Those of them, they can be mapped as spatial network. And as you know, spatial network is a kind of graph structured data. Also, people's movement from origin to the destination can be mapped as flow graph as well. In this context, graph database is a great option to represent spatial data based on the connections in real world. However, it is mainly used for managing semantic information so far. So I think it is a bit difficult to get an idea on how to use the graph database in spatial context. Before introducing several examples of spatial applications, I'd like to talk about issues to use the graph database in an effective way like this. At first, we need to think about how to model the graph database using various types of spatial information. This issue is related to the relevant information and extraction from multiple sources, or it may be discussed with the database construction efficiency. That is, like we need to develop some kind of automatic construction method or something. And also we have to think about how to derive the node and relationship with properties from the spatial information, and also how to organize those kind of spatial information into the graph database should be addressed continuously. Concurrently, we need to think about the purpose of using graph database, where to use the graph database in spatial fields. For example, because of its flexibility, we can use the graph database for the data integration tests. And also, based on the structure of database, we can apply this graph database to the graph-based learning tasks such as XAI, and also it can show good performance for the complex queries without any complex joins. Therefore, spatial query based on relations is a proper cases for using the graph database. Considering these issues, and I'd like to introduce some topics and examples based on the reviews of various researches, including my research. What spatial information can be organized as a graph database? For the first example, I'd like to talk about the indoor space modeling. Multiple sources can be used for organizing as the graph database. For example, we can use BIM IFC files because they have multiple hierarchies, and based on these deep hierarchies, we can create kind of metadata graph for managing those data. And also based on the spatial relations which is stored in the IFC files between building objects, we can create some kind of a spatial network using the graph database as well. Also, we can adapt geometric network structures as well. It means we can convert existing built network data into the graph database, then use the graph database. Nodes and edges in the spatial network respond to the node and relationships in the graph database, or according to the data, they can be mapped based on the line graph concepts as well. As another example, indoor GeoML, the standard of indoor data exchange, defines multi-layered model with geometry, topology, and semantics of indoor environments. Graph database is a good option to integrate those various informations. So referring to the concept, indoor GeoML files can also be used for sources to model the graph database or the indoor environment. These figures are from my previous research on automatic construction of indoor graph database from the floor plans. I adapted the geometric network model concepts. Then, using the floor plans, I made a kind of indoor spatial network like the above figures. And then, based on this spatial network model, I constructed the indoor graph database like the bottom figures. These indoor graph database can be utilized for applications such as routing like these figures. Similar to the indoor, I transformed the OSM network to the graph database like this blue part. And then I selected the indoor entrance node and the outdoor closest node, then connected those two nodes using the single relationship like these figures. After integrating those two indoor and outdoor data, which was independently constructed and with different spatial extents, after integrating, then I applied some shortest path finding algorithm using constructed graph database. And this figure is one of example of optimal routes from using the graph database. Like my case and the other case, like these figures, the graph database based on indoor models can be used for organizing spatial information or a kind of spatial queries such as routing applications. Not only for the indoor modeling, we can use graph database for the outdoor space modeling as well. Let's think about the spatial network on global scale. For the global scale, it has really large volume and complex relation-based structures. It means we can organize both large network data as a graph database for efficient management. Especially based on the flexible schema, there was an attempt to use graph database for integrating various data. For example, BeamGIS integration problems. Knowledge graph is an emerging topic of research field recently. The data of knowledge graph can be constructed using the graph database also. And in the spatial fields, spatial inference and reasoning is emerging as well. Accordingly, there is a demand for constructing the graph database reflecting some kind of spatial context and knowledge. For a specific example of knowledge graph with spatial context, several geospatial knowledge graphs have been constructed and improved as well. These kind of geospatial knowledge graphs are configured with geoentities, which is the physical object in real world with location information, and also they include some kind of geo events as well. So these kind of geospatial knowledge graph can represent geographic knowledge about geoentities and spatiotemporal events. Therefore, they can be used various kind of geospatial question and answering systems for the base database, and also we can get the answer about like what administrative districts belong to Seoul and what is the spatial relationship between Korea and Jeju by the process of spatial inference and reasoning. For another example, spatial data like OSM are used to enrich existing semantic-centered knowledge graphs, such as Wikidata and the DBpedia knowledge graphs as well. Typically, knowledge graphs are used for many recommendation systems, including POI recommendations. My current research is related to this spatial application. The existing knowledge graph is normally focusing on the semantics of users and services. But I think when targeting to the places and the POI, the spatial aspects should be considered. When people find some places, they consider many aspects of places. Let's talk about this example. Where are the restaurants with friendly staff? I want to visit on this evening for having delicious steak, but I want to go there within 10 minutes, like this. When people find the best place, they consider the value of features of places like a restaurant with friendly staff, and also do they provide any delicious steak like this? And also temporal aspects is important, like available time, like in this evening, in this example. So at the same time, people find a place because they want to visit those kind of places. Therefore, spatial condition is critical, such as good locations or shortest time to go there. Even they think about how to go there. It means like they need some kind of route information as well. Related to this topic, currently I'm doing research to construct spatial and semantic integrated graph database using multiple sources of both spatial and non-spatial information. So now I'm trying to address challenging issues about what kind of spatial information that I need to organize into the graph database in an effective way. and how to model those information into the graph database in proper ways, or some of those kind of issues I should address continuously. For the next example is about the machine learning field. The graph database is emerging in machine learning and XAI fields as well. Because of its structure, graph can provide explainable data using some kind of data lineage approach. It means we can manage data flow for understanding the current issues based on the structure of graph. Then we can understand how data was created and what process data went through and where data was used or something. Based on the understanding of understanding of the data, explainable prediction can be realized by following data with their connection to others, which is stored inside the graph structures. For the last example, I'd like to talk about utilization of graph database for the practical analysis based on the graph theory. For example, using crime data of traveler and those criminals' travel data, graph database could be built for crime detection and predictions. After constructing the graph database using some kind of spatiotemporal crime data, and then we can apply some kind of path analysis to find the graph patterns of criminals' behaviors, and then based on those pattern analysis, travelers whose behavior patterns are similar to criminals could be detected or something. For another specific example, I'd like to talk about the trajectory modeling using the graph database. Normally, trajectory data can be mapped as node and directed at just like this concept of figure. So, and those kind of nodes and directed edges can be mapped as the essential elements of property graph model, which are nodes and relationship with properties. Therefore, we can use the graph database to manage those kind of spatial temporal trajectory data efficiently. And after constructing those graph database using the trajectory information, we can use those database for tracing system or some kind of positioning systems as well. For a specific example, actually there were some kind of researches about the COVID-19 tracing system. They used the graph database for organizing the trajectory data. Then you apply some kind of pattern analysis or some kind of graph analysis. They detected people and spaces in contact, focusing on relations between entities, which is stored in the graph database. This figure shows the basic schema of graph database for London's tube network. Like this figure, like this example, the graph database also can be used for managing and analyzing of transportation data as another example as well. In summary, we've talked about the high flexibility, high data intuition, and good performance of the graph database. Based on the advantages of this graph database, it can be a good alternative for managing spatial information for relation-based analysis. However, especially for the spatial application, we should think more about the usage of graph database. Graph database cannot be the substitute of existing spatial database, but some spatial data is much suitable for managing and organizing with graph database. And also, complex spatial analysis is limited in Neo4j or other graph database management system yet. But some of analysis, especially based on the graph theory, are performed much faster and better with the graph database. So in conclusion, before using the graph database for our own spatial purpose, we have to think about what kind of spatial information can be used for organizing as the graph database. And also we need to think about how to model the spatial data to the graph database in the proper ways. And finally, we have to think about the purpose of graph database. It means we need to think about where to use the graph database. These are references of my presentation, and this is end of my presentation. So thank you for your attention.
Thank you very much, Seula. I think that's a really excellent overview of graph databases for those of us who aren't so familiar with them. And I think particularly for those of us who are used to things like PostGIS, been using them for many years, it's really good to see the strengths of each one highlighted. If you have questions, as we've said before, please post them in the chat. I think everybody's maybe a bit shy this morning. I have a question for you, Seula, if we can kick off. So you mentioned the strengths and weaknesses of graph databases versus SQL databases or relational databases. Are there any cases where you would use both? And is there any research into kind of how you have integration between data stored in a relational way or in a graph database way?
So actually, I'm just thinking that based on if the data has some kind of graph structure, it can be mapped with the graph database efficiently. So in that case, I can organize those kind of graph-based data to the graph database. But basically, normally some kind of spatial operations, such as like how can I say, it's about the they cannot support the various coordinate system or something like that. So before I make the graph database, I do some basic spatial operations like calculate some kind of geographic distance between some unit segments or something like that, and then I just store those kind of information to the property. And then I organize those information to the graph database like that. I think this is the kind of the use of both spatial database and the graph database together like that. And also I think it depends on the data. Some data is more proper to be organized with the graph database, but something. Especially for 3D cells or something like those kind of models is more appropriate to the spatial database. So we need to choose which data can be modeled with the graph database and which data can be modeled with the spatial database, and the step of the analysis which can be done by using the spatial database, and the other further analysis can be performed based on the relational analysis. Like that, yeah.
Okay, thank you. We have a question from Nilofer. Can graph database work with unstructured data sources? Unstructured data sources?
Yes, for example, normally graph database is used for the semantic analysis, like irregular data set from the texture data. So, for example, I've talked about the recommendation service and the knowledge graph as well. In that researches, they use the graph database to organize some kind of texture information, such as place descriptions or the kind of user reviews as well. And they extract some information. It is related to spatial or not, but they extract some useful information from those kind of irregular data sets, and then they make it as the graph database together, yeah.
Okay, thank you. I can't see any more questions coming through on the chat. Before we draw everything to a close, just a couple of announcements. So I put a link in the chat box to a special issue that we ran in the ISPRS International Journal of Geographic Information. The closing date was last year, but there's I think 23 papers published in there in the subjects of deep learning and computer vision for geoinformation science. So have a look at those. They may be of interest if this talk was also of interest to you. And Professor Tao Cheng also has an announcement about a special issue that she's running. So over to you, Professor Cheng. You're muted at the moment, Tao.
Let me share the call if that's okay.
Yeah, I've put a link to the call in the chat.
Yeah.
Yeah.
Just share. Yeah, so Yeah, so this is, thanks, James. So this is a special issue really related to pandemic. It's really quite broad, although we call human mobility, anything related to mobility and the pandemic, I think it could be within this this special issue. So it's pre, peri, or post. We're not really there yet for post, but well, anyhow, so yeah, I know there's lots of papers that has been published around this topic, but as I said, hopefully there's something not just about the flow and more about, say, you know, inside it, not about the mobility. So it can be linked to social demographics, can link it to policy, can link it to safety. Can be lots of things. So do feel free to submit the paper. And although the deadline is approaching, so yeah, so really welcome the worldwide submission. And there's one more thing, I haven't put my acknowledgement for my talk. And so as you can see, currently that's our team, and James is there. And yeah, so I think the talk today is relevant to a few PhD students have just finished in the past years. So thanks for their work, and yeah, so thanks again. Yeah.
Thank you, Tao, and thank you everybody again for coming. It's really great to see so many people here, and I think if you want to ask any questions about any of the stuff that you've seen today, I'm sure that Professor Cheng and Seula wouldn't mind being contacted via email. So I just wanted to say thanks again, and we'll, I think, draw the talk to a close there. If you want to, you can use the reactions button to give the speakers a round of applause. And thank you very much again. I'll say bye.
Thank you for your time and your patience, and for James for organizing it. Thank you.
And thank you also to our volunteers who helped to coordinate the session, and they can turn their cameras on now to wave, I think, and we'll say thank you to them.
Thank you so much. Thank you so much.
They're behind the
Professor.
scenes. They're very
James.
modest, but thank you very much. We really appreciate that. Okay.
Thank you so much.
Thank you.
All right.
Thanks,
Bye, everyone.
bye.
Okay, thank you for listening. Thank you.